This is the display panel from an Apple Thunderbolt display, and that's the model that Apple sold from about 2011 to 2016 that used the DisplayPort connector that actually had Thunderbolt 2 traveling over the DisplayPort connector. So these displays are a generation old now, but they're still very viable and they look really nice. If you're interested in what these displays can do, I have another video where I converted that DisplayPort connector to USB-C and converted the Thunderbolt 2 to Thunderbolt 3/4, which is what modern Macs use. So go take a look for that if you're interested. The reason I have this display here is I found it in e-waste, and it was in e-waste because the LCD panel that's on the front of this was broken. So I've actually got this stripped down to be just the LED backlight, and I want to use it as a light for my workspace. One nice thing about these panels is that they have all these layers of plastic diffusers built into them. So the light is thrown in all directions. There's no bright or dim spots when you look at your computer display, which is what you want. And I thought that might be nice for a workspace where I'm going to be doing a lot of detail work and I don't want glare and reflections and that sort of thing. So the idea is that I'll power this independently and hopefully I'll be able to dim it and brighten it, and I'll hang it above my workspace as just a general lighting source. So this video is meant to explain what I've been able to figure out so far about how the LEDs are arranged in this, and then step through the process as I convert this into something that I can power independently. If you're interested in doing something similar, this panel isn't all that special, but I will show you the model number on it. So it's an LM270WQ1. And this was used in iMacs as well as the Apple Cinema display, the Apple Thunderbolt display, of course. It's a 27-inch panel size, and the submodel here, the SDB3, that's the one that was specific for the Thunderbolt display, but they're all quite similar. I think those designations have to do with maybe the brightness or number of colors it can display. That doesn't matter in this case because I only want the LED functionality from it. So let me zoom out and I'll show you what I've been able to figure out so far. The LED light source is actually down along here. When I flip it over, it'll make more sense. This is the right side and this is the left side as you're looking at the original display. And the LED strips are down here and down here. There's actually two different strips, a left side strip and a right side strip. Each strip has 36 LEDs placed on it. And then those 36 LEDs are grouped into 3 groups of 12 LEDs each. Each one of those groups of 12 wants 36 volts to operate. And that makes sense. That would be 36 volts divided by 12 LEDs to give you 3 volts per LED, which is very standard. This is the connector, and I'll zoom in so you can see it a little bit better. It's kind of like, I think, maybe a Molex connector. I'm not sure, but it's not the 0.1 inch spacing that we're used to on like breadboards. A lot of the jumpers that I have are meant for breadboards, and a lot of them don't fit in here, but I actually do have some that have a little bit finer tip on them, and I found that I was able to use these. So if you're looking at this connector, of course, this connector comes out the right side of this panel if you're pretending you're looking at the original display. And so it starts with the left side, and it starts with positive and then goes to negative, positive, negative, positive, negative, on down. And then these 6 wires would be for the right side. That's probably hard to imagine. So let me just demonstrate that by plugging some in. So here's positive on the very end connection there, and then I'll give it a negative. And so that will be lighting up a single group of 12 LEDs on the left side of the panel. And I'll go ahead and also plug in a positive and a negative for the right side of the panel. So I'm only lighting up one group on the left and one group on the right out of the total of 6 groups. So I'll zoom out again, and here's where I'll use my power supply to connect these up. You could use any power supply as long as you can limit by well, I should say voltage and current. In this case, I have found through experimentation that you can just limit the voltage, and the current will be limited by the LED strips themselves. So I've got this set to 36 volts, and I will just stop this down to half an amp. So when I flip this on, let's get it all in view. Okay, there's the whole panel along with my sketchy little wiring here. Okay, when I flip this on, the entire panel turns on. And you won't be able to necessarily see exactly what I'm seeing because the camera that I'm using is adjusting so quickly to the light. But I hope that this is clear that I'm lighting up the entire panel all at once. And I'll turn it off again. And now I'll power up just the right side. So I'm going to unplug the wires that went to the left side, and I'll power it on again. And you'll see that just the right side is powered up. And there's a really even gradient from light to dark here. But of course, remember that the whole point of this is that it's a diffused light panel. So it's throwing the light everywhere. So even though it's lighting up just the right side with LEDs that are on the right side, the light is really getting thrown everywhere. I'm currently showing a little under 36 volts at 230 milliamps. According to the data sheet, these 12 LED sets should require 36 volts per set at about a maximum of 350 milliamps. So what I'll be doing is I'll be taking those groups of 12 LEDs and putting them in parallel so that I can provide 36 volts to all of the groups at once. And theoretically, that power should even out, or at least even out smoothly enough for what I need, and show the same brightness on every single LED. I'll have 350 milliamps per group of 12, and there's 6 groups of 12. So 350 times 2 is 7, times 3 is, looks like 2.1 amps potential at 36 volts to power up this panel. And then I'll also want to be able to reduce the brightness. And so a little bit of testing here shows that I can do that by limiting the current. So here's currently only taking 260 milliamps. If I start turning that down, I can pretty easily, and with fine control, dim the panel down to where now it's just barely on, and that might be useful. The first thing I want to do actually is to get rid of this connector, which is smaller pitch than I'm used to working with, and the 0.1 inch pitch is something that's I've got a lot of parts for. So I think what I'll do is try to install one of these connectors. It's called a IDC connector, and I've got a little set of them here. Here's an IDC connector. It's got 2 rows, and the rows go to these kind of cutters on the back that will go into the wire, and you can see they're staggered. So this one is actually for 16 pins, but it's just 8 pins wide by 2 pins deep. I only need 12 pins, but this connector looks like it'll really nicely crimp into the wire size, the gauge of wire that's already on here, and then it'll give me an interface that I can connect into. So here's my crimping tool. It is nothing fancy at all, but the way these work is you just set this, the actual connector, and then this back strap. Normally you'd go around a ribbon cable, and you would just push these together, and then you use the tool here to crimp it down. In this case, I've actually got 2 ribbons, and they're not exactly the same size as my other IDC ribbons, so I'm going to try to fit these kind of manually over each wire and then see if I can crimp it down. Okay, so I think I have an IDC connector crimped on here correctly, and the next thing I need to do is just make sure I haven't accidentally shorted any of these cables together. And actually I think I can leave the original on there too because it's not really in the way. But let me see if this connector has any shorts. It'll be kind of boring, but I just need to basically test every adjoining pin to see if they're shorted together. I've tested all of the pins that are in here against their neighbors, and also tested the new crimpings against the original plug, so that I know that I have a good continuity between, you know, say pin 1 and pin 1. And so I'm happy with the crimp, everything went well. So now that means I can use sockets that match the IDC connector on the other side, and then those sockets themselves can fit into breadboards and that sort of stuff. So let me go grab one of those next. Here's an IDC socket with right angle pins, so that's kind of convenient. I can plug that in like that, and then that would work, for example, on a breadboard like this one. I can take this IDC right angle connector, and it wouldn't have to be right angle, a regular straight connector would work as well. I can actually connect it to this 2-slot section of the breadboard, which is all positive on one, all negative on the other. And the reason that will work is that these pins alternate positive, negative, because of the way that they interface, you know, the parallel connections to the side-by-side pins on the ribbon. Okay, so now I can test to make sure that I've got negative and positive right. There's the negative side. And so that should be every other one of these, starting with the last one. No positive, yes negative, no positive. So that all checked out right. So we don't have any shorts from positive and negative, but now let's check to make sure that all the positives really are connected. So now we're going to get we're going to start at this end, and every other one should be positive. True, negative, positive, negative, positive, negative. All right, so we've got a good set of connections here, and we can give power to this the screw terminal sort of header on the end, and that should power the entire display. And I want to use wires which are a little bit more substantial than just jumpers, so I'm going to use these DC barrel connectors. This plugs in my power supply, and then I'll wire this into the terminal. Okay, I think we're set up to test. So let's zoom me back out and bring the power supply back into view. So now I'm going to use these short leads with the barrel connector. We'll flip it on. We'll set it to 36 volts. We'll see what happens. Get ready for a major correction of the iPhone light balance here. You might not be able to see anything, but we are set for 36 volts, and I better crank up the current. Let's start with, let's just start safely at 100 amps or 100 milliamps. I don't expect anything to turn on. Wow, it turns on already. So that's 100 milliamps. Let's go to 2, 3, 4, 5, 6. And I've actually hit the limit of my, my power supply here at just half an amp. So peculiarity of the power supply and which mixtures of volts and amps that it wants to do, but it won't do 36 at 2.1. So what we can do instead is switch over to another power supply I have. It's one of these. So this is a much more powerful one. This is 36 volts at 5 amps, so that should be plenty. Now, you may recall from earlier, I only had to set the voltage and the current actually self-regulated, either due to resistors that are on the LED strips, but more likely just because of the number of LEDs that are in series, maybe limiting the current, but I'm not quite sure. But I did find that there were no problems with excess current, even when it was unrestricted. So this is a 2.5 and this is a 2.1 millimeter. I can plug them together. Oh, that was interesting. Yeah, they're not making a good connection. So I'm gonna get my adapter for 2.1 to 2.5. Okay, so they look cobbled together, but here's a 2.1 millimeter that plugs into the panel, and it goes to one of these XT60 connectors, like on an RC application. And then I've got the opposite, which is a 2.5 millimeter for the power supply side, and it goes to the opposite XT connector. So here we go. Let's see if through all these adapters it works. Wow, look at that. Full power, full brightness. That is bright. Really happy with that. So I'm curious at how much current we're running. So here's my low current clamp meter. I really like this one. It just goes up to 10 amps and has a nice low current resolution. So we'll flip it on to DC amps. And there's another video that I've made where I actually calibrated this so that it's 0 all the time. But for maximum accuracy, we can set it to 0 and it'll show us the differential voltage. So let's plug it in. We need to go positive here, out negative on the bottom in terms of power flow from the supply. So we'll go positive to negative. We don't have a lot of wire split to deal with, so let me open this up a little bit. All right. So positive to negative. There's no way to get this to you. Let me zoom in and see if that helps at all. Okay. So there we go. There's 2.09 amps. Now 2.1 amps is what I calculated at 350 milliamps per set of 12 LEDs. There we go, 2.1 amps. So that's exactly the amount that's predicted at 36 volts. So let me unplug it again here. Looks like we're successful. I have, this little board is really just kind of for trying it out, but I think I could cut this down and actually use this, maybe with some shrink wrap, as my permanent power connector. Somewhere along the way, I want to set up current limiting, either through like a buck adapter or some sort of small power supply that has a provision for a pot or for PWM signal. Ideally, I would limit current to properly dim these, but yeah, it looks like I've got all the LED lights wired up correctly at least, and that's what I was seeking to do with this first step, so I'm happy with that. Once I had the light actually working, I turned my attention to how to hang this thing from the ceiling, and fortunately it has these threaded holes all around the perimeter of the frame, which take, I believe they were 3mm screws. So I found some screws that fit and some lightweight chain from a hardware store that I can use to hang it. This is actually called lamp chain some places, or else jack chain, so that's exactly what I need here. But yeah, just screwed it into the sides there, and that'll be plenty for hanging this up, and adjustable as well. Next, with a lot of measuring and a stud finder, I found the two best rafters to attach these hooks into in the ceiling. These rafters are 24 inches on center, and the 27-inch monitor works out to about 25 inches wide, so that works out pretty nicely. Now it's time to actually hang this thing on the hooks, and this is definitely going to be awkward. But I did make two little marks in the chain while it was down on the desk to let me know which hooks of chain I should hook around the hooks in the ceiling. All right, that I don't want to do more than I have to, but it works. I found a power supply online that might be exactly what I need, so let's see how it works. This is actually a variable voltage power supply, but depending on how it's implemented internally, who knows how they're actually limiting voltage. It may actually be curtailing current, maybe using PWM. I'm not quite sure, but it's limited to 2 amps, which is good because my panel, as I showed earlier, pulls 2.1 amps at maximum. So it's actually going to make the panel last a lot longer if I use just a little bit less current. And by having the maximum be 2 amps, there's no risk of turning this up too high. But it has this nice knob, goes 3 to 36 volts. Of course, 36 volts is the max for the panel. And yeah, it couldn't be simpler. It even comes with a bunch of adapters. So I'm going to try this sucker out. Okay, so we've got a 2.5 millimeter, it's a 5.5 by 2.5 millimeter output on this variable power supply. And I've got adapters set up to run that through my little power meter here, little inline power meter, which will show voltage and current. And then out of there into the 5.5 by 2.1 millimeter plug, which goes into the panel. I don't know why there are two barrel connectors, which are so similar. It's so frustrating because they look identical. Sometimes they plug together depending on which side you've got on which end. And you can get a 2.1 male into a 2.5 female. It'll plug together, it'll have a loose connection, and it'll drive you crazy. Okay, let's plug this in to AC. And what's nice about this knob is it actually has an off position. So it starts out off, and then there's the click, and it turns on. So I'm at 3 volts. We're coming up to the level where my inline meter can actually sense what's going on. And I'm gonna flip the panel over, so bear with me. Now's a good time to mention that Captain Tape is your friend. Put this on the back of this little board here so that there's no way I accidentally short it out by sliding it across the back of the metal panel or anything like that. Let's go ahead and turn it up and see what happens. We're 21. Of course, we wouldn't expect it to come on until the forward voltage is reached for these LEDs, and there we go. So 30 volts. I'm seeing the very beginning of some light on the panel. And you can't see any of this because the panel is so darn bright. Let's bring these up into view. So I'm at 36 volts. We're not pulling the full current yet. And of course we have adapters and limitations, resistance. It's all kind of messy here, but let's turn it all the way up and see what happens. Okay, so there's maximum. We're at 36.3 volts, 1.85 amps. We're obviously not getting the full 2.1 amps or even the 2 amps that this power supply says it allows, but this appears to be a really effective way to dim and control the light. Or who knows, maybe I'll just crank it up every single time. That would work too. When I connect directly from the power supply to the device with just this one connection, minimizing the resistance along the way, I get more current than I saw measured earlier through all those different adapters. Not to mention an inline adapter is always going to use a little bit of power too, so that's something to keep in mind, but we're down in the weeds. For actually wiring up the panel in the ceiling, I'm using this old phone cabling that I have lying around. It has 4 copper conductors inside, so if you double them up, because I only need positive and negative, then that gives a good amount of copper to minimize voltage drop over distance. I'm wiring in 2 wires each into the terminals on this DC barrel jack adapter, and this is what it actually looks like on the ceiling. So I'm using the same kind of approach to wire in 2 wires each into the terminal block on this board that started out as my test board, and like so many things, now it's the permanent one that I'm actually going to use as well. Cable goes up and around. I've got some cable clips holding it to the corners of the walls. It goes underneath my desk where it meets up with the DC barrel jack for the DC power supply, this variable power supply that I've got here. I attached it to the upper shelf of my workbench here, and it's all wired up pretty neatly so that I can just reach over and crank on that light. And you can see it shining down here now. So what's the reason, or what's the advantage of this kind of light versus just some other workstation light? Well, this is the light that I use lots of times. It's just an LED kind of array there. And if I pass my hand across the desk, you'll see that significant shadow. Let me get something down here to simulate some fine detail work. Say I'm working on a SMD soldering or something. If I move my hand along, you see just how much shadow there is there. But if I turn this off and then crank up the new diffused panel, do the same thing, you can see there's far less shadow. I didn't want to post this video until I had actually used my new diffused light source for a few different projects and validated that it helps me work on this bench, but I have to say it really does. I'm really excited about how little shadow there is. I can get my head nice and close in on whatever I'm working on, and I don't have my head blocking the light, and I feel like that's really improved the level of quality that I can accomplish on this bench. I'm also really happy with how well this little controller worked out. Super simple, just to reach over, turn it down, find a dimmed level that I like, or just crank it all the way up. So that's working really well. If anybody's interested in doing the same, and if you've got a 27-inch monitor lying around or even a smaller one, I'd really encourage you to try this out. It's super straightforward to do. and it'll really, like I say, increase the quality of work that you can do. So nice little improvement. Hit that like button if you're at all inclined, but in any case, thanks for watching.